Alright, in today's lecture, we're going to go over mass, length, time, and force, as well as their units. We're going to go over both SI units and English units. Because our physical quantities are related by definitions and laws, we really actually need a relatively small number of physical quantities to conceive of and measure all others. So these are called our primary dimensions. Others are measured in terms of our primary dimensions. These are called secondary dimensions. So for example, length and time are primary, whereas velocity and area are secondary. So once a set of primary dimensions is adopted, we can have a base unit for each primary dimension, and then all other units are derived from these base units. So in the SI system of units, it takes mass, length, and time as our primary dimensions, and regards force as a secondary dimension. So we have mass in kilograms, we have length in the meter, and we have time in seconds, and we have temperature in Kelvin, which we're going to define in our next lecture. So in SI units, force is an SI unit of force is called the Newton. It's a secondary unit derived from the base units for mass, length, and time. It's based on Newton's second law of motion, which states that a force acting on a body is proportional to the product of its mass and acceleration, or my net force is proportional to my mass and my acceleration. And actually, the way that Newton is defined is it's defined such that proportionality has a proportionality constant of 1. So that's where we get our famous F is equal to ma. So the Newton, which is given the symbol capital letter N, is the force required to accelerate a mass of 1 kilogram at a rate of 1 meter per second. So we get that 1 Newton is equal to 1 kilogram times 1 meter per second squared. So again, 1 Newton is 1 kilogram meter per second squared. SI units are nice, lovely, everything works out. But we also deal with English units in this class. The English base unit for length is the foot, not inches. So 1 foot is actually equal to 0.3048 meters. 1 foot is also equal to 12 inches. Again, the foot is the base unit of length in the English system, not inches, even though inches are commonly used. The base unit for time in the English system is still seconds. The base unit of mass in the English system is the pound mass, which 1 pound mass is equal to 0.45359237 kilograms. Now, if you have already taken fluid mechanics, you might be asking me, don't you mean it's the slug? Well, the difference between the English set of units and the British set of units is the fact that English units mass, the pound mass is our mass-based unit, whereas in British units it is the slug. So I typically try to write pound mass as lbm to distinguish it from a pound force. The book just writes lb for pound mass. It writes lbf for pound force. So now that we have the base units of mass, length, and time, we can define force the same way we did for SI units. So in English units, the unit for force is our pound force, or lbf. and it's the force required to accelerate 1 pound mass at 32.1740 feet per second squared, which is standard Earth gravity. So we have that 1 pound force is equal to 1 pound mass times 32.174 feet per second squared, which is again 32. So 1 pound force is equal to 32.174.2 pound mass feet per second squared. Please remember, 1 pound force does not equal 1 pound mass. This will trip you up in tons of your problems. A pound force is not equal to a pound mass. So, as a quick example, if I wanted to determine the weight of an object whose mass is 1,000 pounds, at a location where the local acceleration of gravity is 32.2 feet per second, what am I going to do? Well, my weight is equal to my mass times gravity, which is equal to, no, this is 100, sorry, there's a mistake right here. 100 pound mass times 32.0 feet per second squared. Note that my units right now are in pound mass foot per second squared. I would like my answer in pound force, so I'm going to say that 1 pound force is 32.174 pound mass feet per second squared, which gives me a weight this is 1,000 of 994.59 pound force. This is called your gravitational constant. It's a unit converter. So it's going to convert our defined units of force and its base units. So GC is a proportionality constant. So in SI units, GC was equal to 1. In English, GC is equal to 32.174. These units are very, very, very important in this case. So the last bit of this lecture is going to be about specific volume. So we defined, everyone knows what density is. So from the macroscopic perspective of matters, we're going to consider everything to be universally distributed within a region. The correctness of this idealization is our continuum hypothesis. When substances are treated as a continuum, it's possible to speak of their intensive thermodynamic properties at a point. So thus, at any instance, our density can be defined as the limit as our volume goes to an infinitesimally small volume of our mass divided by volume. So the density is the mass per unit volume. It's an intensive property it can vary from point to point. So the units, so in SI it's the kilogram per meter cubed, and in English it's pound mass per foot cubed. So specific volume, which we're going to use a lot in this course, is defined as the reciprocal of density. So specific volume, which is a lowercase v, is 1 over our density which is equal to our volume divided by mass. We're going to deal with a lot of specific properties, which basically means we're dividing an extensive property by mass. So the specific volume is the volume per unit mass. It's an intensive property, and its units are, so in SI, it's meters cubed per kilogram, and in English, it's feet cubed per pound mass. In certain applications, it's actually convenient to express things on a per mole basis. If you remember, a mole is the amount of a given substance numerically equal to its molecular weight. So this relationship can be expressed as N, which is our number of moles, is equal to our mass divided by our molecular weight. The number of kilomoles in a substance N is attained by the mass in kilograms by our molecular weight in kilograms per mole. The units of mole are the kilomole or pound mole, and for our molecular weights, it's kilograms per kilomole or grams per mole or pound mass per pound mole. If a property is listed on a per mole basis, we're going to put a bar above it. So for example, V bar is our specific volume on a per mole basis. So this bar means per mole. So our specific volume on a per mole basis is our molecular weight times our specific volume on a mass base, on a per mass basis. That's it for this lecture. In our next lecture, we're going to go over pressure.